you're supposed to calculate the final angular velocity. So I'm calculating the initial angular momentum. The initial angular momentum is moment of inertia of the system multiplied by the initial angular velocity. Li is L1 is I1 omega 1. So I can write this as L1 is I1. I1 is moment of inertia of platform plus moment of inertia of each mass. The moment of inertia of platform is 7.6 plus moment of inertia of each mass, it's m, multiplied by r square, where r is 90 centimeter. So I'm taking it in meters, so it will be 0.9 square plus moment of inertia of another mass, or I will write this as this is I1, which is moment of inertia of platform plus moment of inertia of each mass. I'm multiplying it by 2 multiplied by the angular velocity omega. So this IP is the moment of inertia of platform, which is 7.6. M is this mass and this is R1. I'm calling this as R. That's initial. Finally, what happened? This man folded his hands. Finally, this man will fold his hands. So when this man folds his hands, the radius is R2 now. The separation of the masses from the axis of rotation is R2. So you can write your final angular momentum will be, the moment of inertia of platform is not changing, this is final. And this much distance is 20 centimeter. So that's moment of inertia of the platform plus twice of mass multiplied by R2 square multiplied by omega 2, that's the equation. Since there is no external torque acting on the system, in the absence of any external torque, its angular momentum will remain constant, which means L1 will be equal to L2. I can equate L1 and L2. So this is a platform. On the platform, there's a man. He's holding two weights in both of hands. The separation of each weight from the man is 90 centimeters. So 90 centimeters is basically the length of his arm. So initially, the whole platform along with man is rotating with some angular velocity. This angular velocity is given to be 30 rpm. The initial angular momentum is I omega. This we did in the last lecture, that angular momentum is moment of inertia into omega. Moment of inertia of the system is moment of inertia of platform plus twice of mr1 square, where mr1 square is moment of inertia of each weight multiplied by omega. Now, finally, in the final case, this man just fold his hand. When he fold his hand, this separation will decrease. There is no change in platform, so moment of inertia of platform will not change. Just the moment of inertia of these masses will change. So that is 2m r2 square, and obviously angular velocity will change. That's why I'm taking omega. The system is isolated, no external torque is acting on the system. That's why L1 will be equal to L2. So when L1 is equal to L2, you can write this as IP, moment of inertia of platform, plus 2m r1 square omega 1 is equal to IP plus 2m r2 square into omega. Now I'm substituting all values. Say here IP is 7.6 plus twice of mass is 5 kg. R1 is 90 centimeter. If I convert this 90 centimeter into meter, it would be 0.9 meter. 0.9 square multiplied by omega 1, that's 30 rpm. So I'm not converting rpm in radian per second. So my final answer of omega 2 would be in rpm only. So I'm taking this as 30 rpm. And again, your IP here is 7.6. It's 2, mass, which is 5, R2, which is now zero point 0.2 square into. So from here, you can easily calculate your omega. So before starting rolling, you need one more topic, which is known as radius of gyration. The radius of gyration is related to moment of inertia, basically. So when we do moment of inertia, we see that moment of inertia of each shape is different. Like for a sphere, moment of inertia is different. If you take a ring, then moment of inertia is different. For a disk, you have separate formula for moment of inertia. So this radius of gyration, using radius of gyration, you can use a single formula for moment of inertia of all bodies. For ring, for disk, for sphere, for rod, for every body, you can use a single formula if you're using radius of gyration. So see what radius of gyration says. Say you have a body of arbitrary shape and size. This is the axis about which this body is rotating. So I'm calculating moment of inertia about this axis only. So for the whole body, I can consider a point where if the whole mass of the body is supposed to be concentrated, this is the point where if the whole mass of the body is supposed to be concentrated, then moment of inertia of this point will be same as that of body. I'm repeating again. Is a body, it's rotating about this axis. I'm calculating moment of inertia of the entire body. And the formula for moment of inertia will depend upon the shape that you are taking. Now I've just put this body aside. On this body, I choose a point. I give entire mass of the body to this point, and I'm saying that the moment of inertia of body will match with the moment of inertia of this point. So I'm comparing the moment of inertia of body with the moment of inertia of a point. And this point is not center of mass. The separation of this point from the axis of rotation is known as radius of gyration. Is it clear? Did you get this thing? It's not center of mass. In center of mass, we do concept of center of mass for translational motion. But this topic we are doing for rotation. So through this point, we are replacing the moment of inertia of the body. The separation of this point from the axis of rotation is known as the radius of gyration. So the definition is radius of gyration of a body about its axis of rotation can be defined as the distance from the axis of rotation at which if whole mass of body were concentrated its moment of inertia its moment of inertia about the given axis would be same as with the actual distribution of mass. The actual distribution of mass. So this K is basically the radius of gyration. So in terms of radius of gyration, moment of inertia of every body is mk square. In terms of every body, the moment of inertia is mk square. So using this relation, you can calculate radius of gyration for any body. Like if I take this example, ask you to calculate radius of gyration of a disk mass m and radius capital. So if I take a disk, a disk of mass capital M and radius capital R, you're supposed to calculate the radius of gyration of the disk. So for radius of gyration, you can use this simple trick that moment of inertia is always equal to mk square. So for disk, the expression of moment of inertia is mr square by 2. This you will equate it mk square. This m will cancel this m. So this k is r by root. So in terms of radius of gyration, moment of inertia of every body is mk square only. It's independent of shape and size of the body. But the radius of gyration will have different values. Like for the disk, this is r by root 2. Similarly, you can calculate radius of gyration for a sphere. Calculate. Okay, calculate this for sphere and tell me the answer. For sphere of mass m and radius capital R. And take this sphere as a solid sphere. See the simple calculation. I is mk square. For solid sphere, this is 2 by 5 mr square, which is equal to mk square. You can cancel this m with this m. Your k comes out to be r root over 2 by 5. So this is the radius of gyration of the solid sphere. So this is how we calculate radius of gyration of any body. Just equate its moment of inertia with mk square and you will get k radius of gyration. The next is rolling. The next topic is rolling. See, rolling is basically the combination of translation as well as rotation. So if I'm saying that a body is rolling, so if a body is rolling, we can take rolling as combination of, if a body is rolling, that means it's rotating as well as translating. Like if this pen is rolling, that means it's rotating as well as translating in one direction. So it's rotating with an angular velocity omega and it's translating with a velocity vcm. So if a body is rolling, you can break it into two parts. You can break this thing into two parts. It will translate as well as rotation. So you can break rolling into two parts, in translation as well as rotation. I'm considering 3 points on the body. This is point O, this is point A, and this is point B. So if this body is rolling, that means its center of mass is moving in straight line with the velocity vc, and also it's rotating about the axis. So for the translation, each and every part will have same velocity due to translation, and that velocity is vcm. Each and every point due to translation, it will have same velocity, that's vcm. So when I say vcm, vcm means velocity of center. In NCRT, rolling is not given in very much detail. But in numericals of NCRT, to solve numericals of NCRT, you need rolling in very detail. So I have no idea how much detail your teacher have given you. So I'm taking this rolling in full detail. If I just take the theory of NCRT, it will hardly take 20 minutes. But with that theory, you cannot solve the numericals of NCRT. To solve numericals, you need a very in-depth understanding of rolling. So I'm taking rolling in full detail. So it will take maybe 1 hour. It will take 1 hour to complete this problem. So this is translating, means each and every part is moving with a velocity vc. In translation, each and every particle have same velocity. Now, due to rotation, this is point A. If you can remember, if a body have angular velocity, then due to angular velocity, it will also have linear velocity. If this is rotating with an angular velocity omega, then due to this rotation, this point A will have a tangential velocity, which is basically r into omega. If I'm saying the radius is r, then it will have a tangential velocity r omega. This r omega is tangential velocity. R omega is tangential velocity. Similarly here, R omega is a tangential velocity. R omega is tangential velocity. This is it. So if I take this point A, rolling consists of both translation as well as rotation. Due to translation, velocity is vcm. Due to rotation, the tangential velocity is r omega. If you can see, both the velocities are in same direction. So in rolling, velocity of point A, which I can say VA, is basically the sum of VCM and R omega. That you can say it's VCM plus R omega. That's VA. This is VA, which is VCM plus R omega. In the same way, for point B, can you guess the velocity of point B? Just superimpose these two velocities, VCM and R omega.
Yes, sir. It will be VCM minus RW.
Very good. VCM minus R omega. That is velocity of point. Because these two velocities are acting in opposite direction and these two velocities are in same direction. So it's VCM plus R omega and VCM minus R omega. So this is how we calculate velocities in rolling. Is it clear?
Yes, sir.
Yes, sir.
Rolling is basically combination of translation as well as rotation. So whatever you have to calculate, if you have to calculate velocity in rolling, then that is the combination of translation as well as rotation. Similarly, you can calculate acceleration in rolling. So just note it down. Then this is, wait, just write heading like velocity in rolling. Write this heading, that velocity in rolling. The next is acceleration in rolling. Now, you people know the complete mechanics one now. You have done each and everything in mechanics. Can you tell me the number of accelerations in rolling? In rolling, you were having two velocities for each point, right? One due to translation and one due to rotation. This is rolling, which is equal to the sum of translation and rotation. We were having two velocities in rolling. One due to translation, that's velocity of center of mass, another tangential due to rotation. So in rolling, this is the acceleration of center of mass. This is the angular acceleration alpha. Can you tell me the number of accelerations acting on the system? Is just two or someone else? There's one more acceleration. Yes,
Centripetal acceleration.
centripetal acceleration. There will be one more acceleration, which is centripetal acceleration. This is my point A. This is point A. So there is one tangential acceleration of due to translation, each and every point will have an acceleration, which is acceleration of center of mass. Yes, we will have three accelerations. Due to rotation, this will have one tangential acceleration, which is alpha into r. And again, you will have one tangential acceleration, which is alpha into r. The radius of the path is capital R. This is the radius of the path, which is capital R. There's one more acceleration, which we call centripetal acceleration. This acts along the radius towards the center. So if I want to calculate the net, and similarly over this point B, you will have a centripetal acceleration. So net acceleration in rolling, at point A. So you will have three accelerations. The net acceleration is the sum of acceleration of center of mass plus the tangential acceleration alpha r plus the centripetal acceleration AC. This is centripetal acceleration. This is centripetal acceleration. This is acceleration of center of mass. And this is your tangential acceleration. So if you see this thing very carefully, the angle between ACM and alpha r is 0 degree. They're acting in same direction, but this centripetal is acting at 90 degree. So for the net acceleration, you can do one thing. You can add this ACM and alpha r directly because they're acting in same direction. So you can add them up directly. But with their sum, this AC is making an angle of 90 degrees. So to add this AC, you have to use parallelogram law. If you have two vectors which are perpendicular, then the resultant is root over a square plus b square. So you can write this as this is root over square plus the square of centripetal acceleration. So this is the net acceleration. There is one term which is known as pure rolling. So see what is pure and impure rolling. Pure rolling means the contribution of translation and rotation is equal. So if a body is getting same contribution from translation and rotation, then that rolling is pure rolling. So to differentiate between rolling and pure rolling, I'm giving you three examples. A car is running on a road. It's a concrete road. The tire is rolling on a concrete road. Usually in concrete road, the rolling is pure rolling. Means the contribution from rotation and translation is same. Now suppose this tire of the car gets stuck in some mud or sand. This tire gets stuck in sand. Then what will happen? It will rotate a lot, but translate very small, very little. This is concrete road. On concrete road, the contribution from translation rotation is same. But if this tire gets stuck in sand or in mud, then it will rotate a lot, will have a lot of rotation, but it will translate very little, will have very small translation. So in this case, rotation is greater than translation. So it's not an example of pure roll. In the same way, so I'm just writing this example. The car is rolling on concrete road. So translation is equal to rotation. The contribution from translation and rotation is same. Translation is equal to rotation means distance covered in translation is equal to distance covered in rotation. I will explain what I mean by this distance. Distance covered in rotation. So this is an example of pure rolling. This is pure rolling. Throughout NCERT, the major stress is over pure rolling. But there could be other cases like if tire stuck in sand. Then in this case, translation is less than rotation. The tire will rotate a lot but translate very little. Similarly, if tire skid, if you apply brakes on the car and it skids, then during skidding, the car rotates, the rotation is less as compared to translation. So in that case, you can say that translation is greater than rotation. So this is not even pure rolling. So pure rolling is the case. So if you want to get detail of pure rolling, I'm giving you example of take example of this bottle. To understand pure rolling, take example of this bottle. I mark a point here. It says somewhere here I mark a point over the bottle. Say this is the point. This is the point of the bottle. If this bottle is in pure rotation, then after one complete rotation, this point will come back to its original position. Now, can you tell me the distance covered by the point in one complete rotation?
2 pi.
2 pi r. Distance, not angular displacement. Distance. After one complete rotation, this point will cover a distance of 2 pi r. Is this rolling or pure rotation?
Rotation.
This is pure rotation. But if this bottle starts rolling, that means along with rotation, this bottle will move in the forward direction also, right? It covers some translational distance from this point. So this after one complete rotation, it covers some translational distance also. If that translational distance is also 2 pi r, then you would say that this is pure rolling, otherwise not. I'm repeating again. I take this bottle is in pure rotation. In pure rotation, if I take this point and this point come back to its original position, then the distance covered by the point is 2 pi r, equal to the circumference of the bottle. But this is pure rotation. But if I'm saying this bottle is in rolling, that means along with rotation, this will also translate. Like this will come here. So from here to here, this bottle have covered some translational distance. So in one complete rotation, if the translational distance covered by the bottle is also 2 pi r, then you will say that bottle is in pure rolling. So this is how we will use the concept of pure rolling in calculation. So in pure rolling, this is the point. If I take this point on the body, this is point A, this is point A, and this is point A. After one time period, this point will cover the radius of the bodies R. It will cover translational displacement of 2 pi r. Translational distance covered by point in one complete rotation, and the time taken in one complete rotation is represented by t. In time t is 2 pi r. This is pure rolling. So if a body is completing a translational distance of 2 pi r, then this is pure rolling. So through this distance, we can calculate the velocity of center of mass, because center of mass have moved from here to here. Center of mass have also calculated the distance 2 pi r. So velocity of center of mass in this case is velocity of center of mass is its distance upon time. So it's 2 pi r divided by t. This 2 pi by t can be written as omega, angular velocity. So you can write that your VCM is omega. Say tangential velocity was omega r, but velocity of center of mass is omega r is only in pure rolling. This result is valid only for pure rolling. Only for pure rolling. I'm repeating it again. V is equal to omega r, tangential velocity. This is valid for all types of cases. If everywhere in circular motion, tangential velocity is angular velocity multiplied by the radius of the path. But velocity of center of mass is omega r. This is valid only in case of pure rolling. If the tire of the car gets stuck inside the mud, then this relation is not valid. When the car skids, this relation is not valid. This relation is valid only if your car is in pure rolling. So you can get few conceptual questions on pure rolling. Like in pure rolling, I'm calculating some velocities in pure rolling. In pure rolling, velocity of point of contact of body and surface is 0. So this is the surface. And this is the body. This is the radius. I'm calculating velocity of this point. If you can remember, in the last section, we have calculated that this VA is its VCM, angular velocity. VA was VCM minus omega. In pure rolling, you can write that your VCM is omega. So if I substitute all these values here, then you will finally get that your VA is omega r minus omega r. Your VA comes out to be 0. So in pure rolling, the velocity of point of contact of body and ground is always 0. Whenever a point came in contact with the ground, its velocity is 0. To rotate this body, you need torque. So here, friction will apply torque. For rolling, you need torque. So if your body is moving, say the velocity is in this direction, then friction will act in this direction. Then a torque will act on the body. So in rolling, friction will apply torque. This could be your objective questions or conceptuals. Friction will apply torque. But since the displacement of this point is zero, the point which is in contact with the ground, the velocity of this point is zero. If velocity of this point is zero, that means displacement of this point is zero. So if displacement is zero, then you can say that work done by friction, work done by friction is zero. Work done by friction is zero. This is it. So in rolling, the work done by the friction is zero. So you cannot have rolling on a smooth surface, because for rolling, you need rotation. For rotation, you need a torque, and that torque is applied by friction only. So rolling is not possible on a smooth surface. This is also a question in NCERT. Rolling is not possible on smooth surface. You cannot roll a body on a smooth surface, because for rolling you need friction. Okay, the next topic is kinetic energy in rolling. Okay, before kinetic energy, just do one question. I take this body, this is the surface. This is the radius R. This body is rolling with an angular velocity. I give you a point C here. This separation is R by 2. The velocity of center of mass is Vc. I need velocity of point C. Calculate velocity of Vc. C. Velocity of point C. Yes, Noor, you are correct. Noor is correct. Velocity of point C is velocity of center of mass plus tangential velocity. Tangential velocity is omega r by 2. That's it. This is how we calculate velocity in rolling. It's velocity of center of mass plus tangential velocity. And see, if the body is moving in this way, then the tangential velocity in this direction. The radius is r by 2, so this is omega r by 2. You have a point D here. This is r by 3. Yes, no. Now you are correct.
VCM plus R into 3W plus 2 by 6.
Hmm? Why? What is 2 by 6?
Sir, I added both R by 2 plus R by 3.
Would we consider distances from the center only? R is
Okay, so it will be
R by 3.
R by 3.
Right.
Yeah.
You will add or you will subtract it. See, velocity of center of mass is to the right hand side. If body is rotating in this way, Sania, what's the direction of tangential velocity? Tangential velocity is to the right hand side or to the left hand side?
Right hand side.
Right hand side. Say this body is rotating in this way. And at this point, tangential velocity is to the right hand side. But at this point,
Left hand side.
left hand side. So this is your tangential velocity. You're saying r by 3 omega. Now tell me, you will add them or you will subtract?
We'll subtract them.
You will subtract them. You're acting in opposite direction. Next, we have kinetic energy in rolling. Okay, so when we do rolling, we have two types of kinetic energies. So in rolling, the kinetic energy in rolling is sum of kinetic energy of translation plus kinetic energy of rotation. The sum of kinetic energy of translation and kinetic energy of rotation. So kinetic energy is rolling is the translation. The kinetic energy of translation is half m v cm square plus kinetic energy of rotation is half I omega square. If you want, you can convert this thing in terms of radius of gyration. This is expression of kinetic energy slowly. You can even simplify this thing. You can write your I as mk square, where k is radius of gyration, where k is the radius of gyration. If I substitute all these values here, then kinetic energy in rolling is half m vcm square plus half m k square omega square. So the kinetic energy in rolling is, I can take half as common. In fact, m will be common, and we are left with vcm square plus k square omega square. So if you want, you can even convert this omega in terms of vcm. We know that in pure rolling, vcm is equal to r omega. So you can write your omega as the ratio of vcm and r. This is your omega, which is vcm by r. So if I substitute this omega here, then you will get that kinetic energy in rolling is, it's half m vcm square plus k square vcm square by r square. You can take this vcm square to the left hand side. So the kinetic energy in rolling is, it's half m vcm square, it's 1 plus it's k square divided by r square. So this is how we calculate kinetic energy. But remember, this relation is valid for any type of rolling. You can have pure rolling or not. But this you can use only for pure rolling, because in this expression I'm using this thing. This is for pure rolling. So this expression, even this expression can be used for any type of rolling, even if it is not pure rolling. Even if translation is not equal to rotation, you can use this expression. But this is valid only for pure rolling because I'm using this equation. This is valid only for pure rolling. So one question on kinetic energy of rolling. So this is an inclined plane. The inclined plane, the angle of inclination is theta. The height of the inclined plane is h. From this inclined plane, I am releasing three bodies. I am releasing a disk, a ring, and a cylinder. A disk, a sphere, and a cylinder is released from top of inclined plane. Top of inclined. So I'm releasing these three bodies from the top of inclined plane. Calculate or not calculate, compare their velocities compare their velocities at the bottom. So at the bottom of the inclined plane, you're supposed to compare the velocities. All bodies have same mass and same radii. Have same mass and radii. All of them have exactly same mass and same radius. So when you release all these bodies from the top of the incline, you can say that potential energy, when bodies are here, this is potential energy. When it reach at the bottom, the whole of potential energy get converted into kinetic energy. So to calculate velocity, I can simply use conservation of energy. Using conservation of energy, I can simply write that potential energy is exactly equal to kinetic energy. Potential energy is mgh. Kinetic energy is half m. It's rolling. So it will be half m vcm square 1 plus k square by r square. See, this m will cancel this m. We can calculate this vcm square. So vcm square would be, it's 2gh divided by 1 plus k square over r square. So if you want, you can even calculate VCM. For VCM, you can take root on the left hand side. So your VCM is, it's root over, it's 2gh divided by 1 plus k square over r square. This is the velocity of center of mass. It's root over 2gh by 1 plus k square by r square. Next, you can do one thing. This is a general expression for all the bodies. So for calculate precisely for disk, precisely for a sphere, precisely for a cylinder, and I haven't mentioned that this sphere is solid and this cylinder is solid. So for disk, you can substitute k equal to, we just have calculated the radius of gyration of the k of this disk, which was r by root 2. You will substitute the value of k this and you will get the velocity for the disk. For solid sphere, you can write your k as, we just have calculated this was r root 3 by 5. So you can substitute this value of here and you will calculate the velocity of center of mass. For cylinder, if you have a solid cylinder, the radius of gyration is same as that of the disk. So okay. Noor, in the question is saying that from the top of the inclined plane, you are releasing a solid sphere, a disk, and a solid cylinder. They will roll down, and when they reach at the bottom, you're supposed to calculate their velocities. So to calculate velocity, there are plenty of methods. The easiest one is conservation of energy. When all these bodies are at the top of the incline, then the energy they have is potential. They are at rest, so kinetic energy is 0. But when these bodies comes at the bottom, one at a time, like first of all, disk will come, then you will release sphere, then you will release cylinder, one by one. When the body comes at the bottom, then potential energy is zero. That whole of the energy is kinetic. So you can say that your potential energy will be converted into kinetic. So the VCM is its root over it's 2gh by now I'll substitute these values. It's 1 plus k. K is r square by 2 now because k is r by root 2. Then r square. This gets cancelled out. So your VCM is its root over it's 2gh by 1 plus 1 by 2, that's 3 by 2. 3 by 2. So the velocity of center of mass is root over 4 by 3gh.